Thank you very much. My name is Daniel Rode. Thank you very much for introduction. I'm working for Symeo. We produce radar sensors for the industrial use, particularly in the field of share industry. This is our leading market. Radar, I'm sure that you're all familiar with it from television, in marine. The radar is used there, aircraft, etc. Radar, but industrial radar is not that known yet. I studied high frequency technology 20 years ago, and I did that because high frequency technology is somewhere in between electronics engineering and magic. And it still has a magic component as this topic, but in 20 years' time, it's lost its magic a bit. I'd like to explain you radar physics a bit, so that we have a common understanding of what radar is, what are the properties of a radar system. And I'd like to explain the basic principles. A radar sensor sends electromagnetic radio waves that disseminate away from the sensor to the environment, usually directed into a certain direction. It hits upon objects. These can be walls, people, targets, objects of whatever kind. And the radio wave is reflected and it gets back to the sensor. It is received again, and the signal is processed. A part of the signals goes through the objects. For instance, if you have a plastic object, large parts of the radar signal go through, part is absorbed, so that we can get back different quantities of received signals that we can use for evaluation. What do we evaluate? A radar measures the duration of the electron, how long it takes to get to the object and back. And in the air, it's usually the speed of light. This spreading speed, and in other materials is less. If the object moves, there is the Doppler shift, the frequency shift. This means the signal that's reflected gets back in a different frequency as compared to the frequency it was sent out on. For instance, if you see an ambulance passing by, if it's approaching you, it's a higher frequency, and when it drives into the other direction, the sound is different. This is the same principle, and thanks to this shift, in addition to the distance, you can also measure the speed of the object. So there's we hit two birds with one stone. Some maths is needed, although it ruins the magic a bit. This is the equation. The equation describes the ratio between the output sent by the radar sensor to the share that is reflected back. And as a sensor manufacturer, of course, I want to optimize what I receive back. There are different possibilities about how I can do this. This is the equation. This is one example. This is the reflection property of my objects described by radar cross-section. So this means the possibility of an object to cast back. For instance, here you've got a fly, which is very small, hardly any moisture, a very small radar diameter cross-section. It would be difficult to see a fly with a radar. If you specialize on it, it would be possible. There are other objects like a container vessel. It's a huge metallic object with a huge radar cross-section, and it's that's easily to be seen by radar. This is why radar is used a lot in marine activities. There are only objects like vessels, and they reflect very well. And there are things in between. For instance, the human being. The human being has a radar diameter that you can see here. That's a medium good target, if you will. The radar depends on the frequency regarding the reflection capacities. If I want to see a poor reflector, I can go up in my frequency, gigahertz, or a lower terahertz, and I can also see bad reflectors. So the radar is very flexible. As a sensor manufacturer, we operate in the steel industry. In the steel industry, there are huge production halls, dirty, very bad conditions, and I want to make a positioning of cranes, for instance, across the hall. This means I need a high reach, but a high range. But if I need a high range, I have to make sure that the power that gets back is big. What the result that is reflected is big. So what I need to do is to have a higher output. The more I transmit, the more I get back. Unfortunately, there are limits because we have a radio regulation. There are radio bands that stipulate how much I can actually send. I can't send out a kilowatt, for instance. We are in the milliwatt range for safety reasons. Kilowatt would be harmful, although we don't have ionizing radiation here. But there are some limits also from a regulatory point of view. But in order to improve the reach, I can also improve the antenna and the bundling of the beam of the ray. I can also change it and increase the range. A trick to increase the range is to reduce the frequency. The lower the radar frequency, the higher the reach. This has some disadvantages we're going to speak about in a moment. This is not, if you want to do that, it's not a good solution. But physically speaking, the lower the frequency, the higher the reach, for the reasons you're all aware of. As I said before, a fly is a bad reflector. Plastic is a poor reflector too. There is a penetration so that radar targets have many different properties. I can use that to optimize the robustness of the radar sensors. I can put the sensor into a plastic substance, it would work. This and I will not have any performance restrictions. Dust, for instance, if dust is dry, it's also transparent for radar. It doesn't hurt. We have sensors that we use that have been in the steel plant for 10 years with a lot of dust on them, and the customer hardly remembers that they ever installed it. So you don't need to calibrate, you don't need to clean, you just put the stuff there and you forget about it. And this is also the reason why we make progress so fast in that niche, because many other sensors don't have that robustness. Then there's another example, ports, for instance, container terminal. It's raining cats and dogs. Moisture coming from the ocean drops up poor radar targets. Snow crystals, that's no problem for radar, for instance. But if I have a liquid film that can't drip, then it gets difficult. If I look up with a radar and there is a water accumulation, the radar can't measure anymore. But until that point, we are weather independent. Here I can give you some examples of materials and the transmission behavior of the materials. At the top, we see metal, which is our traditional reflector, which is conductive and highly reflective. There is no penetration. The radar signal can be shielded with a thin aluminum foil, and then you can't measure anymore. On the other hand, we've got the optimal medium, which is vacuum. We hardly ever have a vacuum in practice, but we have air in practice. And this is very close to a vacuum, and it basically doesn't dampen. In the middle range, there's also material like wood, dry wood, thin wood. That's great, hardly visible on the radar. Moist wood can be a target. For instance, in the wood industry, if I look at the sliced wood and there's some residual moisture, I can identify it as a target, and I can position the wood log if I need that in the wood industry. And I said that radar uses radio waves. As I said before, the radio frequency range was kilohertz in the past, and today it's all the way up to UKW 100 megahertz and up to that range. And where do we apply the radar? Here the dotted red line shows the area. The radar exists across a high frequency range because there are many different applications. At the bottom, you see the 10 megahertz with very long wavelengths. There is over-sea horizon radars. These are military radars that can cover thousands of kilometers and can detect where there are bending effects so that they can follow the curve of our planet. That's very interesting, but doesn't have anything to do with our use of radar. On the other hand, there are industrial radars like we use them, frequencies of up to 120 gigahertz, and there will be more gigahertz coming. And we operate in the millimeter range regarding our waves. This has pros and cons. I'm going to speak about that in a moment. In the middle range of the spectrum, we have the rain radar. I'm sure you all have a weather app, and you might be wondering what the rain radar actually is. It functions according to the same principle, but is reflected by the reflection takes place from the clouds. So it's not a high reflection but it's enough, the drops that are there, to determine the precipitation, 6 gigahertz. Our rain radar operates at 6 gigahertz, more or less. There are some exotic applications nobody would have thought about that. There are geo radars with which you look into the ground and you can determine the underground. Maybe you can find gold, but that's not what we use it for. But for inspection of railway lines, for instance, is the underground stable? Is there soft material? And this allows you to make conclusions about the depth, but also, is it stone? What are we talking about? Georadar, very different application. We are mostly working in the field of industrial radar, but I'd like to give you an example. On the left-hand side, you see the Oversea Horizon radar, which is located in Russia, and it broadcasts at 15 megahertz. This means it has a wavelength of 20 meters approximately. And this means if I have a big wavelength, I need a big antenna. And the antenna determines the size of the radar. And here, if you take this example, we have a special antenna that has a certain directivity. And in this picture, you see if the antenna size would be hundreds of meters. This is for the low-frequency radars with a high wavelength. But if you look at the right-hand side, you see the other side of the coin, or of the scale. Here we are at 120 gigahertz. And what you see here, this is the antenna on the right-hand side. So the antenna in such a system can be located on one chip, that is 1 square centimeter of size. With that, you can have low-cost, compact sensors that you can implement. It's much cheaper than what you see on the left-hand side, just because of the material and what it costs. The question is, time and time again, is it dangerous? No, that's a cliche. Radar isn't dangerous. But there is the legend that radar would be dangerous because of the irradiation. And in the past, radar was generated with tubes. X-ray tubes. Today we take transistors, and the tubes had residual radiation, and that was X-ray, and that's dangerous because X-ray is an ionizing radiation. It's destroying our cells. Radio waves are not ionizing, and this is why they don't make an impact on our cells. And radar also regulates because it can also heat. Microwave, for instance, the microwave is a similar frequency as the radar, but with much more performance, much more power. This is why you shouldn't bend over and look into it like on TV. But then radar is harmless. 100 milliwatt in particular, that's the maximum if you compare it to the microwave with 1,000 watt, depending on the microwave. This is something I wanted to say. Radar is not dangerous. It doesn't do any harm. What does radar look like? I don't know if you ever looked into the interior of your microwave. It's slightly different. Let me start on the left-hand side. The central element of a radar or component is the antenna. With the antenna, I can do many things. I define the field of view, the bundling, the range, and the aesthetics as well. As you can see here, the antenna is an antenna system. And the next, there is the high-frequency front-end board with another antenna that illuminates the lens from the back, and the lens bundles the signal, bundles the ray into the field of view. There are also front-end chips, and the radar transceiver chip is located there, which we saw in the previous slide. It features the primary antenna that illuminates the lens. When I receive back the signals reflected by the object, I have to do something with it. I have to strengthen the signal, amplify it because it's weak. With high frequency amplifiers, you can amplify the signal. You can prepare it before I pass it on to the CPU board, where the signal is processed. In this most simple case, it's the Doppler frequency shift. That's a simple case. If you want to do more difficult things, you've got more possibilities of things I can do with this radar. I'm going to show you two more slides in a moment. And in our case, we can calculate the speed, and we can calculate the average and other things that are more difficult. And we can also measure the distance. That's our main application, the measuring the distance. That's our main business. And last but not least, of course, there is the interface. We use Profibus. That's an IP connection, if you will, and a power connection. This is necessary, of course, as well. Somewhat, that's enough. The microwave consumes much more. Let me speak about the most essential components that make an impact on the system. I mentioned the antenna before. But what are the parameters the machine design makes an impact upon? The field of view, I mentioned it already. There are competitors that have a very broadly viewing radar. We do bundle the signals to have a longer reach. So if you have a broad view, you can't look that far, so to speak, and the other way around. So you have to make the decision. What should the antenna look like? And this is why that you have the antenna design competence. You need some experience to really produce a good antenna adapted to the use case. This is why the radars look different, because the antenna is always different. This makes an impact on the channel. The antenna bundles, I can look into different directions. In marine applications, for instance, the radars rotate and detect the targets. I have already been speaking about the antenna. You can amplify the directivity, and these are the most important features of an antenna, and what that change the output of a radar sensor. The aperture is something that's also important. That's the ratio between the physical size to the wavelength of the antenna, the physical size. The over-horizon radar with the name of Woodpecker have 20 meters of wavelength, but the antenna is much bigger to bring about the directivity. If you want to have a directional effect, you need a big aperture. You can do that with the antenna, but there are also other possibilities, other methods that might be used. For instance, SRAR. I'm going to speak about that in a moment. One important component are the semiconductor chips. They are crucial. This is the centerpiece of the radar. Whole radar systems can be integrated into one chip nowadays. Here on the right-hand side, you see ND Semiconductor. This is our parent company. They produce radar chips we can use. And there's a complete system. This is called System on Chip, with all the features, with antenna. And we are always waiting for novelties, what our colleagues do. 240 gigahertz, you can see that at the booth in Hall 4, booth 630. So Hall 4A, booth 630, you can hear more about that. Semiconductors are very important for us. The processors are important as well. We need a signal amplification. As I said, this is done, signal processing is done in an embedded way. And we are lucky because the computing power increases because of the smartphones. The computers are more and more performant and cheaper. This means that we are very happy to have number cruncher algorithms, and this will develop towards AI. Radar processing, signal processing with AI is no longer a legend. This is at least the direction we're going into. So semiconductors are very important. Here you see the applications. You find more information at our stand. what we do, why radar, why aren't we using optic sensors. Here you see why it's not possible. There are extreme requirements. It's hot, it's dirty, it vibrates. You need extreme robustness. And this is the reason why we are operating in this niche and why we are very successful in this. Here you see an overview about the different industries where we find these harsh environments. The dirtier, the more Symeo. That is what I used to say. So you always find us where it's really dirty. And these are the industries like harbors, mining, the steel industry. In mining, there's a lot of dust, and this is what we like. What I'd like to do is to give you an outlook. Now you know what radar is. You have found out that you've heard that before. The rain, the radio, maybe your car has a radar. Industrial radar is something you might not have been so aware of. I hope that you've learned something, but that's not the end of the possibilities. I've only been speaking about the basic principle of distance measuring. There are many other possibilities. For instance, imaging. You know that laser scanners, the radar imaging is becoming more fashionable as there is more computing power and cheaper CPUs. Great algorithms are possible, and I can have a look at a broad field of view, and I can look at different targets at the same time, and I can also detect the speed so that I can track the objects. Or classification is also possible with the radar. There are also applications in the automotive industry already. There's another topic which is SAR. Maybe you've heard of that before. Here, the aim is a lateral resolution to improve it by moving a radar past the object. That's tricky to do. Maybe we can discuss that later on also at the booth because I'm running out of time. Last but not least, I'm going to skip this summary, but there's one thing I would like to say, one thing you need to pay attention to. A radar system, that is not the sensor. A radar system is the sensor plus the environment. This means the dissemination and the target is all part of the radar system, and it requires a certain skill to be able to design this radar system, and we think that we have that competence. So I'd like to thank you. I wanted to show you what we are doing in terms of radar, what is happening in the industry in general. This is just the tip of the iceberg. At the bottom, you see that there's much more underneath the water surface. We try to lift the iceberg out of the water, and we'll be excited to see what will be developed in the next few years. One more thing. If you want to experience the magic of the radar, we have a great demonstrator at our booth that features this robustness. But for now, I need to stop. I'd like to thank you very much for your interest. If you have any questions, I'm available at the speaker zone. I didn't want to exert pressure on you, but I'm sure you've got a tight schedule. Yes, indeed. So thank you very much. I will find you in the meet to lead the speaker area for conversations. And you will also be at your stand. It's hall 7A.